students, in this video lecture we are going to talk about wave equation and the solutions of wave equation. So in the last class we have seen that the wave equation, it does admit a unique solution, right? You have a, you can actually talk about if you can talk about a solution. So let's say if there is a solution, then the solution is unique. That's what we have shown. Now in this part, what we are going to do is focus our attention on the existence part. Okay, but if you remember, for the Laplace and heat, yeah, if we wanted to talk about the existence of solution in the initial cases, what we were doing was we were looking for scaling kind of, yeah. In heat equation we looked at some scaling, if you remember, yeah. So basically functions which scale, and then with the help of that we deduce some fundamental solution. And in case of Laplacian also we have deduced some radial function, right? So we were looking for a radial function which are the solutions of the equation, and then since Laplacian is rotational invariant, and then we can talk about the fundamental solution. Here what we are going to do is nothing like that. So as I told you, see, heat and Laplace is they are like brothers kind of, yeah. Wave equation is a different thing, yeah. So in wave equation, the structure is very elegant actually, yeah. So for now, what I'm going to do is I'm going to do it for n equals to 1. So the spatial dimension is 1. Okay, spatial dimension is 1, and after this we will do it for the higher dimensions. So in most of the books, or most of the general courses, the simple course which you do, the first course in PD, generally they treat the n equals to 1 case. Okay, so here we are going to do the n equals to 1 case, assuming that we do not know. I am quite sure most of you do not know even the n equals to 1 case. Okay, maybe you did not study it and in your course. So we are going to do that, and then we will go from there. Okay. So the problem which we have is, if you remember, it is a initial boundary value problem. Okay, so I'm not writing all that initial boundary value problem. So the equation will look like this: utt minus Laplacian of u. Now n equals to 1, Laplacian of u is u xx equals to 0, right? This is in r cross 0 infinity. Clear? And u of course is g. Okay, so you will be given information on u where on the this thing boundary, yeah. So in this case the boundary is of course the base t equals to 0, and you will be given the value of u and ut. Ut is h, right? So this is on r cross t equals to 0. If you remember, in the bounded domain case, in the uniqueness case, what we did is u was g on the parabolic, on the omega t bar minus omega t, right? Yeah. So the closure minus the omega t, and here ut, the information of ut is given on the base. So here that of course that particular thing, because r is unbounded, this is essentially that boundary becomes r cross t equals to 2. Yes. Now here g and h are given. Okay, I am not specifying what they are. For now, let's just assume that there are some g and h given. I want to talk about it. Okay. Now, before I do that, I want to specify another thing. So this is just another reminder. See, the point is this. I don't know whether I have told you guys this thing or not. I should have explained it later before. So see, here in heat, Laplace, wave equation and all of this is required. All of this work has to be done. Why? Because you see, this problem, if I am just asking you to solve it, you guys can solve this problem. Of course you can do it, yeah? But the thing is, the boundary conditions has to be nice. G and h has to be nice functions. Otherwise the problem is, you see, this problem. So for r cross 0 infinity, if this kind of domain is there, see, this problem can be solved by separation of variable, right? Separation of variable. And And I think most of you guys know what separation of variable is. If you don't know, let me write it. It's basically this: u of xt is some function, let's say capital X of x, okay, and capital Y of y. So you are basically capital Y of t, let's say. So basically you are looking for a function which is a function of x times function of y. Now if you put it in the equation, that will split it up into two different parts. One is a function of x, so it will give you two different ODEs. Yeah, with this boundary condition, those ODEs can be solved. Maybe, yeah, maybe. There is no guarantee that it can be. Most of the times with nice enough boundary conditions, we can do it. Yeah. So after that, you do that thing and you get your solution. So on those things you guys already know. Yeah. Separation of variable. One very nice thing about separation of variable is it gives us an explicit solution. Okay. So one nice thing is it provides an explicit solution. Clear? Okay. So it provides an explicit solution, but this is a pro. But there is a con, and the con is a big one. The con is, see, it only holds for domain. So if you don't know, now you know. What I am trying to say is this: what is the main problem with separation of? See, generally what I see is most of the students, whenever I ask to solve some, let's say, heat equation, wave equation, Laplace equation, whatever, they start doing separation of variable. That is not true. You cannot use separation of, otherwise you see there is no point of starting any PD, right? You just do separation of variable, you get a solution and you are done, right? Okay, it is not true, because in most of the time the main problem is this: it does not hold for most domains. Yeah, let me put it this way: most domains. What I mean by most domains is this. See, of course, with this equation, this relation, separation of variable you can use. But the thing is, for separation of variable to work, to get an explicit solution, you need these boundary conditions also, right? These boundary conditions. See, here the boundary is a straight line, or some nice boundary. So you can do this. But in a crazy looking domain like this, you can't use separation of variable, right? Okay. So it holds for most domains. It does not hold. Let me put it this way: it does not hold for most domains. That is, what I meant is, for rectangular domains, or triangular domains, rectangular domain, or disk, or the whole ball in Rn or something like that. Those kind of domains, it will work. It works, but not in an arbitrary domain. Yeah. So, but not in arbitrary domain. In arbitrary domain. So you do realize that this is a big con here. You cannot expect always your solutions to be in a nice domain like this. You cannot expect your solutions to be nice domain like this, or in the whole space. Yeah. So in those cases, what do you do? Then you are just left out with nothing, right? Okay. So these kind of things are used. These methods which I am going to develop now, they will be helpful in those kind of cases. Okay. Which is most of the time, most cases. Okay. Right. So let us come back to the method which I am trying to find here, and this is a very, very simple method. What I am going to do is, see, this can be made more precise, but I don't think that we have the technical capacity of doing that. But I will just write down as much mathematically as possible. So what I am going to do is this. See, if you just write down this equation looks like this, no? Del 2u del t square minus del 2u del x square. Okay. So this is given to be 0. Okay, this is given to be 0. Now you see, you can write, this is this is an operator, of course. This is not a like a square minus b square kind of thing, but you can of course break it up, right? If you just do it, Yeah, I'm not quite sure whether you guys know any algebra on operators or not, but you can write it like this. Yeah, del x del t minus, sorry, this, let me put it as a plus. There's a mistake here, but let me do it like this. U, this is equals to 0. I can write it like this. Clear? So what I'm going to do is essentially I'm going to break. So this operator, see, this operator, you can think of it like this: del 2 del t square minus del 2 del x square acting at u is 0. So that's an operator. Yeah, this is an operator. What is an operator? An operator takes a function and gives you back another function. Here it is taking a u and giving you back another 0. Clear? And giving you back a clear 0. 0 function, not a number 0. Function 0. So everywhere it is 0. Okay. So this particular operator, what I'm going to do is I'm going to break it up into two parts. Yeah. This is mathematically true. You can of course do this thing, but the mathematics which is required for this, we did not do it right now. I don't think that most of you have seen this sort of mathematics, but for now you do realize that it should have been something like this, no? Yes. So this is coming from the algebra of operators. Okay, algebra of operators. Okay, so for now let's just assume this part. Yeah, I don't think that it is very difficult thing for you to assume, but because this is very straightforward, it's like a square minus b square is a plus b, a minus b kind of thing. Yeah, now this again I'm using some definitions of operator here. Okay, so please bear with me here, because this will make life much easier. Now what you do is we set this thing, this particular thing, okay, as some function, let's say v. Okay, so set v of xt to be del t minus del x of u. Clear? So which is what? Which is del u del t minus del u del x. Okay. So see, why I wrote it, I am always using the shorthand notation UTT, UXX. Here I am writing it like this just for you to understand that we can break it up like this. Yeah, otherwise you may get confused. So this is UT minus UX, right? So that's your shorthand notation. This is shorthand. Okay, so V looks like that here, and then so let's say that's your 2. Okay, let's call this as 1. So then from 2, what do you get? From 2, what we get is, one second, let me see. From 2, what do you get? In terms of v, we get this vt plus v of x is 0, right? Because this is v, then this operator acts on v then. Yeah. Okay. So that is 0, right? So let us understand what we are doing mathematically. Yeah. Let's see that we are saying that we are assuming that if you write an operator like this, so basically what we are going to do is, let's say a b times some function f. Yeah, if you have something like this, then I can write it as, I can just leave b out and I can look at a out and I can look at how b behaves with on f. Okay, whatever it does, then I can take the action of a and I can work with that. Okay, so this is, think of this as a definition kind of. Yeah, so I can use that particular thing here. Now once I have this, that is giving going, it's an operator, so it acts on u and gives me some function v. That v, now again del t plus del x acting on v. So that is this. This is equals to the function 0. Okay, right. So now what we are going to do is essentially, you see our equation as we have just seen, it reduces. So let me write down here, otherwise it may get confusing. So the equation looks like this, no? Vt at the point xt plus Vx at the point xt is going to be 0. Clear? So this is for x in R and t greater than 0. Okay. Now, as you can remember, this is a very known equation to us. This is called a transport equation, right? So this is a transport equation with constant coefficients, of course. Yeah. So let's call it 3. Yeah. So 3 is a transport equation. Okay, and the solution of it, and the solution of 3 is given by, how is it given? V of xt. Yeah, so I am going to write the solutions directly, because of course you guys can write it down, right? This is transport equation. You just write down the solution using method of characteristics. Yeah, so it is x minus t. Yeah, what is a? Where a of x is going to be defined as the value of v at the point x0, not the point x0 but on the line x0. Okay, now so it is fine. This is a transport equation and the solution is given by some function of x minus t. Of course, here a is in C1 of R, that is given. Yeah, it will be in C1 of R. So that is your V. Now what is V? V is essentially again since V of xt is defined by del t minus del x of u of xt, right? V is defined by this, right? So if you just put it there, what you have is, it is ut minus u of x equals to a of x minus t. That's the equation which you are going to get. So this equation is in R cross 0 infinity. Clear? Okay. Again, what sort of equation is this? Again, this is a transport equation. The difference, so let's call it 4. Now, the difference between 4 and 3 is this. See, this is a transport equation. Of course, the sign difference is there. But here, it's a homogeneous equation, right? And this equation is not a homogeneous equation anymore. It's a inhomogeneous or a non-homogeneous equation, right? But it's not very, again, the same method of characteristic works here. Yes, you can use the method of characteristics, and let me write down the the solution here. Okay, so here if you want to write down the solution, so one thing, I am assuming this thing. Yeah, I'm not solving this problem because we already did these things in the first week. Yeah, how to solve this kind of problems, using method of characteristics. Yeah, so I'm not going to do this thing. You guys can handle it yourself. I'm quite confident about that. So this is 0 to t a of x plus t minus 2s, okay, ds plus b of, I will write down what b is. Yeah, b of x plus t. And if you do a change of variable, so essentially you do x plus t minus 2z to be 2s to be something z or something. Yeah, then you can just change this variable and you can write it like this: half times x minus t to x plus t. I hope this is fine. Yeah, a of xi d xi. Clear? Why you can write it? Let's say we call this as xi. So you see, at t equals to 0, what is going to happen? So at s equals to 0, this limit will be x plus t, the lower limit, and the upper limit will be at s equals to t, it will be x minus t. Yeah, and ds will be changed to minus 2 d xi, so that half is coming and minus is there, so that is why the limit interchanges, right? Okay, so that's quite easy thing to follow. And plus b of xt. Now what is b of xt? Here this where maybe I can write it here, where b of x, okay, this we are going to define it as u of x comma 0. Yeah, so u of x comma 0, I am defining it like b of x plus t. Okay, once I have this, then you see, now I have to compute. See, I do not know what a, if I just solve, let us understand what we are doing. See, if we just solve this equation, yeah, for just normal this equation, then the solution is given by some function of x minus t, right? This function is an arbitrary C1 function, right? And similarly here also the function which you are getting, see, b A is there and B is there. This B is also an arbitrary C1 function, right? See, this B is in C1 of R. That's these two are arbitrary functions. We don't know what A and B are. Yeah, we have to find what A and B are. To do that, what we are going to do is we are going to invoke the initial and the boundary condition. Yeah, so let's do that. See, the first initial condition, condition gives B of x is g of x. That is quite clear, right? Why? Because on the base u is g. Yeah, because you see at x equals t equals to 0, at t equals to 0, u is g, and by definition that is b. So b is g. Clear? So the initial condition gives b is g. There is no confusion about it. Okay. Now, what about the other one? So let us write it down here. Now I will use the second initial condition. Okay. So the second initial condition will give us a of x equals to v at the point x0. That is what we define. You see, where is it? I defined some. A of x is given by v of x0, right? So a of x is given by v of x0, which is given by ut at the point x0 minus ux at the point x0, right? Because v is given by ut minus ux at the evaluated at the point x0, so this is evaluated at the point x0, and now this is given by h of x. That's the boundary condition given to you. So if you remember, in the boundary ut is given by h, right, minus ux at the point x0. What is u at the point x0? That is g. So ux at the point x0 is g prime of x. Yeah, u at the point the base, in the base u is given by g, so ux is given by g prime. Yeah, just derivative, because we get this g we are assuming here. See, of course the assumption here is h and g, they are smooth. For now we just assume they are smooth. Okay. Now if we substitute all of this in this u, okay, let's say call it 4. Now substituting all this in 4, so substituting a and b in 5, we have u of x comma t, that is given by half x minus t to x plus t, h of xi d xi minus g prime of xi. Okay. So let me write it this way. Yeah, it will be better actually. Minus g prime of xi, this whole thing. Yeah, this whole thing d xi. Okay. Okay, plus g of x plus t. Here. Okay, and hence u of x comma t, that will be given by half g of x plus t plus g of x minus t plus half x minus t to x plus t h of xi d xi. Clear? So this is for x in R and t greater than 0. Okay. This is clear. I just put all the values together and see, u is given by this particular thing, half of x minus t to x plus t xi d xi plus b of x plus t. Okay, so I am just substituting all that value here, and this is what I am getting. Okay, so u of xt is given by half g of x plus t plus, so of course you have to break this up. You see, half g prime of xi, that is given by half g of x plus t minus half g of x minus t with a negative sign. So and then when it get incorporated with plus g of x plus t, then that will give you u of x t to be whatever is written here. Clear? I mean, this is from fundamental theorem of calculus. So let me write it down. This is via the fundamental theorem. So we are using fundamental theorem here on this, yeah, to get this thing. So using fundamental theorem, let me put it this way: fundamental theorem of calculus, right? Of course, here we are assuming G and H are smooth. Okay. Of course, you don't need smoothness, but at least you need G is in C1 because you understand that we have to take derivative. Huh? This formula. So this formula. Let's call it 6. Huh? That's not a. This formula is not a fundamental theorem of calculus. You use fundamental theorem of calculus in this on this domain. Term, huh? And then you get this. Here. Okay. So 6 is called the D'Alembert formula. Yeah, this is very important, and I want you guys to remember this thing. I mean, because we generally use it most of the time without even calculating this thing. So you do not have to calculate all the time. Just remember this thing. This G is the base U at the point x0. Remember this thing, the average of that x plus t and x minus t. You take the average of that, okay, and that G, what is this G corresponding to U at the point x0, and this H you take corresponding to ut at the point x0. Yeah. Okay. Now, before moving on, what I want to do here is this. This is a simple thing, but this is what I need you to check yourself. Huh? Please check this part. Check. See, this is the D'Alembert formula which I derived. Yes, this formula I have derived using method of characteristics. Yeah. Without doing that, you can also derive it. So how can you do that? See, what is the problem you are given? utt minus uxx is 0. Yes. So this in R cross 0 infinity, and u at the point x0 is g, ut at the point x0 is given by h, right? So that is given. X is in R, of course. Not okay. Let me write it. X is in R. Right. Now, see, if you really want to solve this problem, this is what sort of equation is this? If you remember, I'm not writing all that, yeah, but I guess you guys already know. So this is assuming that you guys know canonical form, yeah. So given a given a second order linear equation, so let's say given an equation like this: a of uxx plus b of uxy plus c of uyy plus some lower order term containing ux, uy, u. Okay, this equals to 0. Let's say that's your given equation. Then you can have a transformation. So basically xy going to xi eta. Okay, I'm just roughly revisiting that canonical form. So you have a change of variable. There is a change of variable which looks like this, and if you define w of xi eta to be u of xy, okay, if you define something like this, so define this. If you define something like this, you can show that there exists a change of variable. And how is the change of variable given? Xi of xy, sorry, this is not x. Okay, no problem. Huh? Xi of xy is given by x plus y, and eta of xy is given by x minus y. Okay, with this change of variable, if this equation, so let's say number one, let's say this equation is hyperbolic. If let me, so before this, yeah, assuming, define this, assuming 1 is hyperbolic, okay, that is b square minus 4ac, this is positive. If this happens, okay, then your equation, this equation, let's call it star. So this equation also falls in this category, right? This category, right? Okay, so this star, then star can be written as w xi eta equals to 0, where xi is given by this. So let me put it this way: xi of, this is t, xi of x comma t is given by x plus t, and x comma t eta is given by x minus t. Okay, I hope you understand. What I am trying to do here is this: I am showing you another way. So this is, let me put it this way, another way of deducing D'Alembert's formula. So D'Alembert's formula is from a homogeneous equation, right? So how do you deduce it? See, this is another way. Given a second order equation, linear equation given by 6, okay, you see, you can of course show that there is a change of variable here. So basically the Jacobian of the determinant is the Jacobian of the transformation is non-zero. Yeah, you have a change of variable, and if you define w to be w of xi eta to be u of xy, then of course assuming there is a solution u which looks like that, then let's say this 6 is hyperbolic. This 6 linear equation is 6 is hyperbolic. That is, this equation happens. Of course, star is hyperbolic. See, when is 6 hyperbolic? This is, I am assuming that you guys know what canonical transformation is. Yeah, so this is called a canonical transformation, right? Canonical transformation. Okay. So assuming that b square minus 4ac, let's say here, if b square minus 4ac is greater than 0, then the problem is hyperbolic. In our case, star, b square minus 4ac, c is 0, right? And ab is 1, 1, 1. So minus 4ac is of course positive. See, a is minus 1, b is 1. Okay, so minus 4ac is positive. So the star is hyperbolic. Okay, and then with this change of variable and the defining w to be u, you can actually reduce star to something like this: w of xi eta equals to 0, where xi is x plus t and eta is x minus t. Clear? Now, if something like this happens, therefore, if you want to write it, what is w of xi eta? What is it? It is some function, let's say capital A of xi plus capital B of eta. Clear? For some A, B in C2 of R. Clear? Okay. So you can write W like that, and therefore hence U of xt equals to some function of x plus t plus some function of x minus t. Clear? That is there. Yes. Now what I want you guys to do is this. So I want you to verify this whole thing down. Do you understand what I am trying to say? I want you guys to verify the whole thing. So use a change of variable which looks like this and transform this equation, this star, to a equation which looks like that. Once you do that, w of xi eta will look like some function of xi plus some function of eta. Once, and then you write u of xt to be this. Here, put the initial condition: u at the point x0 is g and ut at the point x0 is 8. So now what I want you to do is this: put the initial conditions on u of xt and deduce D'Alembert's formula. Deduce D'Alembert's formula. Clear? So this is another way of looking at the D'Alembert's formula also via canonical transform. Okay, so now I hope that you are more or less quite familiar with D'Alembert's formula. Let me write down a small theorem here, which will make our claim much firm. So the theorem: assume G is C1 of R. Okay, G is U corresponding to at the point x0. G is C1 of R and H is in C1 of R. So basically I am taking G and H to be C1 and define U of xt to be half of G of x plus t, clear, plus G of x minus t plus half of x minus t to x plus t h of xi t xi. Okay, x is in R and t positive. If you write U of xt like this, then U is given by C2 of R cross 0 infinity. Okay, if you write U like that, then U is in C2. Okay, U is in C2. UTT minus UXX, that is going to be 0. Okay, in R cross 0 infinity. Clear? So UTT minus UXX. So basically what it is saying is U solves the hyperbolic equation in one dimension. U is twice differentiable with respect to both time and space. And 3, how is the boundary condition satisfied? It is satisfied in the sense of limit. So essentially it says that if you take a limit towards any point x naught 0 on the boundary, okay, so basically on the t equals to 0 line, then U of xt get converges to G of x naught. Clear? And the same happens with ut. Limit xt going to x naught 0 t positive, ut at the point xt becomes h of x naught. Yeah, so this is the theorem. I mean, see, we are not going to prove this theorem. There is nothing to prove. U is of course C2. That's quite clear, right? H is C1. So you are taking the integral of a C1 function. That's going to be C2, right? And G is given to be C1, right? G is given to be C1. So okay, I have to take G to be C2. One second. Because you see, U has to be C2 in time and space, right? So every component has to be C2. This component is already C2. H is C1, integral is C2. This has to be C2. I'm sorry about it. This has to change a little bit. This has to be C2 of R. Here, G is C2 of R. C1 is not, sufficient. We have to increase it. It is C2 of R. Okay. Right, now that is there. And what more? What else is there? Okay, so that's this is from the D'Alembert's formula, right? One-dimensional heat equation. This is the solution for the one-dimensional heat equation. Okay. Now, one small remark which I want to put here is this remark. This is very important. Okay. As you know that for a Laplace equation or a heat equation, homogeneous. Okay. So in contrast with a Laplace or a heat equation, okay, here wave equation, the solution of a homogeneous wave equation of is given by u, yeah, in ck provided g in ck and h in ck minus 1. See, if you take h to be in ck minus 1, this integral, the function defined by this integral by fundamental theorem of calculus becomes ck, and this is given to be this part is given to be ck. So ck function and ck function, the ultimate function u is going to be ck, yeah. But you cannot say that it is going to be a C infinity function, okay, as opposed to heat equation. You understand? So in heat equation, that was going to be a C infinity function, any solution, but here it may not be. So if G is Ck, H is Ck minus 1, then U is Ck, yeah. But you cannot say this is C infinity. Okay, so that's a small remark. So this is one very vital, important difference between the elliptic and the elliptic parabolic and the hyperbolic case. Okay, so now I will do something a little different, not very different. I mean, this is for a different domain. Okay, so this is a method which I want to illustrate. So the method is called the reflection method. Okay. So this method I am doing it for this particular domain, and but you guys can use it in many other places also. Okay, so it's not a very it's a very versatile thing to use. So the problem is this: so in one dimension only, n equals to 1 I am taking. Yeah, so let's say you are given this equation ut t minus ux x. This is going to be 0. Yeah. So initially our problem was something like this. See, we were defining the whole equation in this domain, right? In this domain. Okay, that's your t, that's your x. Okay, sorry, I wrote the other way. This is x, this is t. Okay, so this is the whole domain where the problem was defined in the initial case, but in this case the problem will be defined only in this part. Okay, only in this part. So this is in r plus cross 0 infinity. Yeah, this is defined in this. U is going to be g and ut is going to be h on r plus cross t equals to 0. Yeah. Okay. So essentially, this is the domain which we are working. This is the domain, and boundary condition is given only in this part. Only in this part. So u is g in this part and ut is h in this part. Okay, and the equation is also given by utt minus uxx, but only in this part of the domain. So I do not have any information on this. Okay, D'Alembert's formula gives us the solution in the whole domain. Okay, right. Now the thing is, I want to use I want to write down a formula for this problem. Now I need some more information. So where g and h are smooth functions, are smooth. Okay, with this information, g of 0 is equals to h of 0, which is given by 0. This is very important information for whatever we are going to do work. Okay, g of 0. So at the point 0, this point, g and h is going to be 0. Clear? This is the information which you are going to use. Now, see, D'Alembert's formula says that given an equation like this, you have a solution given by D'Alembert's formula, but where in r cross 0 infinity. But here the information is given only on r plus, only in this part, only in this part. So how are you going to? So I have to somehow extend our problem to the whole domain on this part also. Okay, we have to extend it in this part also, and then we can use D'Alembert's, right? How do we do it? So we do it using something called a odd reflection. Okay, we do it using something called a odd reflection. So what we do, we actually set a new kind of function. U tilde of xt is given by u of xt, okay, which is x positive and t positive, okay, and minus u of minus xt for x negative, t positive. Clear? Why we wrote it like this? We want the reflection to be an odd reflection. What is so special about odd reflection? So if you see, if you approach this any point here, so any point, this is see u at the point xt, that this I mean, if you let us take any point here. So any point here, the x part is 0, and this is any t naught, let's say. So 0 t naught. If you are approaching 0 t naught, so u at the point 0 t naught equals to minus u at the point 0 t naught. So on the in the limit, okay, and that will give you u at the point. So in this line, it is going to be 0 kind of thing. You understand what I'm trying to say? Okay. Because 2 0 t naught is going to be 0, and hence u at the point 0 t naught is going to be 0. Okay. So u tilde I am defining it like this, and g tilde also I am going to define. So I am going to write it in the whole domain, that is given by g of x, okay, and this is for x positive, minus g of minus x, this is for x less than equal 0. Okay, and of course I am also going to write what is h tilde. Similar thing, h of x, x greater than equal 0, and minus h of minus x, x less than equal 0. Okay, see, this is an odd reflection. Why we have to take odd reflection here? We actually are kind of forced to do an odd reflection because g of 0 is given to be 0, right? If this is the case, see, if you take x to be up from in the limit, g is a smooth function, right? So I want to extend the function smoothly. Okay, so important thing is extending the function smoothly. Right? I don't want any bump or anything. So g and h has to be smooth in the whole x-axis, right? In order to do that, g at the point 0 has to be 0. Now, if that is the case, you see, g at the point x, limit x tends to 0 plus, okay, this has to be limit x tends to 0 minus. So if g tilde is continuous at the point 0, then this has to happen, g of minus x. Okay, so you understand that g of 0, I mean, so from here, what I want you to do, I mean, you can see that if this is the case, then g of 0 to g of 0 is going to be 0, right? And then g of 0 has to be 0. You understand? That is why this odd reflection. If this is a even reflection, g of x can be some thing other than 0 also. Okay, so it may not work. Yeah. Okay. So this is the case. Okay. I hope this is clear. Why we are taking odd reflection? Because g of 0 and h of 0 is going to be 0. I want g to be 0 at the point 0, and that is why this odd reflection I am taking. Clear? Okay. So essentially, I'm not doing anything. You see, I'm taking a point here. I'm taking a point here. Fix a point here. Fix a point here. Okay. What I'm saying is, let's say what u at this point. What is it? I mean, you also will take the same value here with a negative sign. If you take the reflection of that point. Okay. That's what it is saying. Okay. And the similar thing for g and h. So if you take a point here and if you take a point here, g, whatever value, if this point is a reflection of, let's say this point is a reflection of this point. Okay, you know what g does here in this point, right? You know what g does here. So G will do the exact same thing here, but with a negative sign. That's what it is saying. Yeah, that's the odd reflection. Now, once you have this, now this is a simple thing to note. So note that if you define u tilde like this, then u tilde tt minus u tilde xx, that is going to be 0 in r cross 0 infinity. Okay, please, I want you guys to verify this thing. Yeah, and u tilde is going to be g tilde and ut tilde is going to be h tilde. Okay, on r cross t equals to 0. Clear? So please verify this thing. Please verify. Okay, once you verify this, then you know this problem. I know what is, according to D'Alembert's formula, it is given by u tilde of xt is half g tilde of x plus t plus g tilde of x minus t plus half x minus t 2x plus t h tilde of xi d xi. Clear? And now if I just break it up, I mean, you know, you see, this is for in the whole domain, right? But I want you to I want ourselves to solve this problem in r plus cross 0 infinity. So what happens? What is our original solution? U of xt, u tilde is given by this. So u of xt will be given by two different formulas. Half g of x plus t plus g of x minus t, okay, plus half x minus t 2x plus t h of xi d xi. Please remember, when is h tilde a is equals to h tilde is equals to h if x is positive. So here h tilde, if I can write it as h if x minus t is going to be positive. So if x is greater than equal t, which is greater than equal 0. Clear? Now what about the other case? So other case, this I want you guys to just calculate yourself. I mean, this is very easy. Yeah, I mean, there is nothing much to do here. This is minus g of t minus x. Yeah, this gets changed, t minus x. Okay, because this becomes g of g tilde is minus g of minus x. So that is why this plus gets minus and g of minus x. So it gets plus half x minus t, minus x plus t to x plus t h of xi d xi if 0 less than x less than t. Okay, so for x greater than t, this is the case. For x less than t but greater than equal 0, this is the case. Okay, so this is in a half line. If you want to do it in a half line, you use a odd reflection and do it in this. Okay, so basically what it says is, let's say h is 0, it says that this formula, so let's say this formula is given by, I don't know, maybe 7. Yeah, we did not write 7. So this formula is given by 7. That 7 says that initial displacement g gets split into two parts. Okay, you see g is getting split up into two parts. One is moving to the right, okay, and one is moving to the left. This is moving with a speed 1. So you need, in general problems, the problem will look like utt minus c square uxx equals to 0. So the speed of this wave is given by c, and here c is equals to 1. So basically we say that the speed is given by the speed is 1. Okay, so one wave is moving towards right, moving to the right, okay, with speed 1, and one is moving towards the left with speed 1. Okay. Okay, fine. Now this one small remark I want you to do, and then we are going to end this small video. So let's say remark is this. Note that g double prime of 0 we are assuming it to be 0. Okay. For u to be in C2. So I want my u to be in C2. For u to be in C2, g double prime of 0 has to be equals to 0. Here, because otherwise it won't match here. Here. So this condition has to be required. So please remember this thing. So the condition which we need for this solution to exist is g0 equals to h0 equals to 0 and g double prime 0 has to be equals to 0. Okay, for u to be in C2. Otherwise, this is the solution. Okay, so generally we always assume g double prime of 0 to be 0. Otherwise, you know, we want our solution to be C2, right? Okay, right. So we end it here.